finally met her in person. It's recording. This is a revision seminar for Intro Math Econ Advanced. It's semester 2, 2015. We have one faithful soul left, and we're going to talk about sign diagrams and limits, and see if I can say something helpful. Okay, so I mean, technically I'm calling it sign diagrams and limits because that's how the things that cause pain, but the purpose of this is to try and figure out what a function is doing, basically, at various places. So is it increasing or decreasing or turning point? Is there an asymptote? Is it going to infinity? Is it going to minus infinity? Is it leveling off at a particular point? That's what we're interested in doing. So that's the question that we are asking ourselves, and it hinges very heavily on having an intuition for how functions ought to behave. So a starting point for this is knowing what a polynomial ought to do when you look at it, and saying that x squared ought to have a turning point and x cubed ought to have a point of inflection and that sort of thing. That's the start of it. But it's also to do with the fact of developing an intuition so that you can look at a function, do a couple of calculations and go, oh yeah, I've got a pretty good idea of what it does, without having to draw a graph and without having to get a computer to draw the graph for you, which a lot of people have gotten used to at school, getting a computer or a calculator to draw the graph for you. So that's the philosophy here, is that what's the function doing without using technology, basically. So that's the idea. Okay, so a function might do any number of things, and the hardest part of this, which is why I think I might just talk about this really, the hardest part of this is to know what a function does when you go really far to the left and really far to the right at infinity, and what a function does when it's near a place where it's not defined. So they're the hard bits. Actually, but I might just put a list. We want to know turning points, behavior near the vertical asymptotes, and end behavior. I don't know what your lecturer calls it, but like at plus and minus infinity. Not that x can be plus or minus infinity, so x approaches plus or minus infinity. They're the sort of three main things that seem to be causing the most pain, and they're the things that you're looking for. The turning points, most people are comfortable with differentiating it and setting it equal to 0. Behavior near the asymptotes and the end behavior is a different story. So let's deal with them. So 1, differentiate, set to 0, solve x equals, and you'll get these answers, and these are their critical points. And usually at those points it's either a turning point or an inflection point. It may be a maximum, it may be a minimum, and knowing what the derivative is doing on either side of those points is useful. It may be that you'll also have plus where it's not defined. So you get all these points. Some of them come from the derivative being 0, some have come where the function's not defined, and they're all critical points. The derivative will change its direction, or possibly not, but it's the only places where the derivative could possibly change its direction. So my first pass at doing this would be just looking at that. So if you didn't know about the behavior near asymptotes or the end behavior, you could at the very least look at this. So let me just do an example. something like that. I really hope this doesn't turn to dren. So if I wanted to find the critical points, and draw a sign diagram, I could go, all right, find f dashed x. Now, being a function that's currently written as a fraction, the quotient rule will do the trick. So the quotient rule goes through the bottom squared, and the top starts out with the bottom. So we keep the bottom as it is and differentiate the top, and then we keep the top as it is and differentiate the bottom. And I often get confused when I get that round the wrong way and I differentiate the bottom first. And so my way of reminding myself is that it starts off with the bottom on both the top and the bottom. I've got the bottom squared and I've got the bottom not squared, but also not differentiated. So that's the only way I've ever found of being able to remember which way around it goes. So, yes. And so I've got 2x squared plus 6x minus x squared plus 1. So I've got x squared plus 6x plus 1, which is not going to be fun. I may change the question so that this will work out to something nice. Oh, that you could do that in the exam. Completing the square on this. No, it will factorise, it just won't be pretty. But that's okay. That's not the point here. So f dash. So we're going to solve f dash x equals 0. So that's x squared plus 6x plus 1 over x plus 3 squared equals 0. If I times both sides by x plus 3 squared, I'll get that, and I'll have to solve that quadratic equation. I could use the quadratic formula, or I could complete the square. What's the favoured approach in your course? Whatever you like. What do you normally do? So x is equal to minus b plus or minus b squared minus 4 times a times c over 2a. Now 32 would be 16 times 2. That's the biggest square, I think, that goes into that. And the square root of 16 is 4. So it looks like we get minus 3 plus or minus 2 root 2. Sweet. All right. And also, I just need to go back to my original derivative function and go just to cut and pick a minute. It's not defined when x is minus 3, because x is minus 3 would be keep putting a 0 on the bottom. And so I will start to draw my sign diagram. So here we have minus 3, minus 2 root 2, and minus 3, and minus 3 plus 2 root 2. And I presume I could probably put a minus infinity and a plus infinity in there as well. Is that how your lecturer does it? With the lines?
Yeah. Some of them are double, but not
All right. And so I know that at those points, this one's a double one, I think, because it's not actually defined there. That's how I would do it. So we know that. Have you still got that picture? doesn't matter. I'm going to not draw it that way. I'm just going to do it as a table. So this one, its derivative isn't defined here. Oh, crap. Can I just draw a different picture? I'll draw a picture of my own and then I'll fill the table in later. Okay? I'm just going to draw the x-axis. So here we have minus 3 minus 2 root 2 and minus 3 and minus 3 plus 2 root 2. An important thing is to figure out what order these numbers go in. So you've got your places where the derivative is 0 and the places where the derivative doesn't exist or isn't defined. And you need to know what order they come in. That's very important. And what we have here is that the derivative is 0 here. And here the derivative doesn't exist. And here the derivative is 0. That's the information that we currently have. And we can use that to construct the sign diagram that the lecturer wants. Okay, and so we have 4 zones here. We have one over here, which is to the left. And we have one between these two, and one between these two, and one here. That's 4 different zones. And in each zone, I could figure out whether it was increasing or decreasing. So I know the function's not actually defined at this point. So that's just that little open circles to remind me of that. And I think that's what your lecturer is using as that double line concept. Okay. So let's see. I could figure out whether it was plus or minus by subbing in a point in one of these zones into the formula and seeing what I get. If I had a calculator, I would do that with a calculator. But we'll see what we get. F dash x, just from the previous page. All right, well, let's see. When x is sort of large and negative over this side here, so maybe something like minus 10, I'm going to get 100 minus 60 plus 1, so that's going to be a positive number on the top and it's still going to be positive on the bottom, so it's going to be positive. So I'm going to pick a sort of, I chose minus 10 because it's easy for me to square because it becomes 100. We get f dashed is positive. Alright, so that was in this zone here, so we get positive here, which means it's going up. That's the derivative is positive, by the way. So f dash positive. In this zone here between minus 3 and minus 3 minus 2 root 2, okay, 2 root 2 is more than 1, right? Because root 2 is 1.5-ish. So it looks like minus 4 wouldn't be a bad number to try in this zone here. So I just want to see what happens when it's a little bit less than minus 3. So if it's a little, this is positive no matter what. If it was just a little bit less than minus 3, this would be a little bit more than 9. And this would be a little bit more negative than minus 27. So I'm going to get a negative number. So that's how I think about it. You pick a number that's in here. You could pick an actual number like minus 4 and go, right, minus 4 squared is 16, 6 times 4 is 24. I'm going to get 16 minus 24 plus 1. That's going to be negative. The bottom is positive no matter what. And so that's going to be negative. Or you can try and reason about what it's like to be close to minus 3. That's the idea. Coming down there. All right. So if x is just a little bit more than minus 3, so say minus 2, you've got to be careful because if this was like minus 3 plus half of root 2, or 2 would be too far. Okay. So try minus 2. Minus 2 squared is 4, and 6 times minus 2 is minus 12, so 4 minus 12 is negative. Okay, so it's going to be still negative here. And then over here where it's nice and large, I can put x equals 0 is a great number over there. 2 root 2 is just a bit under 3, so x equals 0 is a good number in this zone. And I get a positive number. So it's going like that. So it's going up, down, and then still going down, and then up. Sweet. That's my sign diagram. I don't know what Virginia's sign diagram is supposed to look like, but that's how I think it through. And if I had to now draw a table, I would make one up that looks roughly right. So that looks about. Yeah. Just going to show everyone this. That's the sort of table that I think Virginia's looking for. Each of the dividing lines between these zones is marked by one of the critical points. So I'm going to copy that. Double line at -3 because it's not actually defined there. And then my f dash x is positive here, negative here, negative here, positive here. Alright, that's not too bad. Can't like it. For me, I would have to draw my little diagram on the other page and then make my table afterwards. But I would actually need to extend my table later anyway, so I would actually do quite a bit of work somewhere else and then finish off my table nice and neat when I'm done. That's sign diagrams for derivatives, and that's pretty much the deal. I think the concept of the double line is when it's not defined there. Okay, so the next stage is us to try and figure out what happens near the asymptotes. So an asymptote is a place where the function approaches it but never gets there. A vertical asymptote happens at the places where the function isn't defined. So we do have vertical asymptote at x equals -3 as undefined there. And so we're very interested in what actually happens at that point. Okay, so here at this point here, at -3 minus 2 root 2, the function is perfectly well defined at that point, and so it will actually come up and then go back down again. So this one here is actually a turning point. The function will come to this point because it's actually defined at that point. So -3 minus 2 root 2, I can perfectly well sub that into the formula and it will come out to something. Not that formula, the original formula. I can perfectly well sub that into this formula and it will come out to something and it will have an answer. And that answer will be a maximum because the function comes up and then turns and then goes down. And over here it will come down and then go up. That's all good. The issue is what happens at this double line where the function isn't defined there. That's a vertical asymptote, and we're very interested in what happens there. So, vertical asymptote x equals 3 because it's undefined there, and we're very interested in what happens as I get close to -3 from this side, and as I get close to -3 from this side. My instinct, based on the fact that it's sloping downwards, is it will go down to -infinity. That's my instinct. So because this is an asymptote, it's likely to go to +infinity or -infinity, and the function is sloping downwards here, so it should go to -infinity. So that's my guess. So let's see. As x goes to -3 from the left, let's see. Right. So, here's where we get into the thing with limits. If a limit is, so if you have 1 over 0, it's approximately, it's infinity. 1 divided by 0. It's infinity in inverted commas. But it depends on which way you go to 0. So if you come to 0 from the negative side, 1 over a negative number is always negative. And so, excuse me, you'll get 1 over a millionth, which is minus a millionth, which is minus a million. 1 over minus a billionth, which is minus a billion, and it'll go to minus infinity. That's the idea behind it. So the closer and closer and closer we get to x equals minus 3, the more we expect this to go to minus infinity. That's how I think about it. Yes, you could do it as a substitution if you like, but I could say as x goes to minus 3, x squared will go to 9, like we'll go to minus 3 squared plus 1, which is 10, and x plus 3 will go to 0 from the left, because x is going to 3 from the left. And so we're going to get that f of x is going to go to 10. Are you allowed to write this? Or is that just really crap? It's 10 over 0. Is that bad? Okay, so we have 10 divided by 0, but from the negative side. So 10 divided by a negative number would be negative, and 10 divided by 0 would be infinity, but it's negative infinity because we're coming from the negative side. I don't know if that's an acceptable way of writing your working, but that's how I'm thinking about it. The top is going to 10, and the bottom's going to 0 from the negative side. 10 divided by negative 0 is negative infinity. As x approaches minus 3 from the right, we get that x squared plus 1 approaches negative 3 squared plus 1, which is 10. And x plus 3 approaches 0 from the positive side, and so therefore f of x approaches plus infinity. That's how I would argue it out if I was going to do it. And so I can go back and fill in my sign diagram, and I'm just going to redraw it. You wouldn't do this in your exam, you'd just do your sign diagram. This was plus, minus. This was going up and actually achieving a turning point and coming down. And this is going to minus infinity. And this is coming down and achieving a turning point and going up, and that's going up to plus infinity. And then the final thing we want to know is, well, what happens at the very, very edges? Behavior at the end of time, so at minus infinity and plus infinity. At the edges of the universe, what happens over there? So we want to know, as x goes to minus infinity, what happens to my function? And this one I am much more certain on. So there are multiple ways of doing this, some less rigorous than others. When I look at this I go, alright, x squared is, if x is like a billion, x squared is way, way bigger than minus 1, so the minus 1 is not going to matter. And if x is like a billion, x is way, way bigger than 3, so this is going to be approximately equal to x squared on x, which is a billion, which is very large, so it's going to infinity. That's how I think about it. The other thing you can do, which is probably a little easier to focus on, is that there is one particular limit at infinity that you definitely know. You know that 1 over x to the n goes to 0 as x goes to infinity. That is something that you definitely know, no matter what x is. No, because it's not no matter what x is going to infinity, no matter what n is. And that's when n is a positive number. So, n positive. You also know that 1 over e to the x goes to 0 as x goes to infinity. So, if I can rewrite this so that it's all in terms of 1 over x to the something, then I'll be good. So being a fraction, I can divide the top and bottom by whatever I want. And so I can divide everything by x squared. Divided everything on the top and the bottom by x squared, by the biggest power that I saw. Not sure if that's something you've seen. Oh, L'Hopital's rule.
Yeah.
No, I wasn't. That's not the same thing. I could do L'Hopital's rule, yes. L'Hopital's rule would do it too, where you differentiate the top and differentiate the bottom. If that's something that's good in your course, go for it. This is the thing I naturally do first. I just divide everything by the biggest power of x that I see. But L'Hopital's rule will do it fine. So to do L'Hopital's rule, you need to do the limit as x goes to infinity. L'Hopital's rule says that if both of them are infinity, or both of them are 0, then you can just do the derivative of the top and the bottom and it'll still come out to the same answer. The function changes its value, but it goes to the same place. So we've got infinity on the top and infinity on the bottom. Differentiate the top, differentiate the bottom, which goes to infinity. Only that will be negative infinity because x is going to negative infinity. And as x goes to positive infinity, same working gives that f of x goes to positive infinity. Alright, so now we finally have the full picture. X, f dash, f and minus infinity as well. So we get plus, minus, plus, no, it wasn't plus, minus, it was plus, minus, minus, plus. Sorry for those back in time there. And so this is going up, down, this is going down, that's going up. This was going to minus infinity here, and it was going to minus infinity here, that's what we just figured out there. Over this is going to plus infinity, and this is going to plus infinity. There we go. So my guess at what the function actually looks like, if I wanted to make a guess, is that I can mark out those points on an x-axis. I haven't figured out where it crosses the x-axis or not, so that's not going to be... but I know that it's got a vertical asymptote there. I know it's going up to plus infinity there, down to minus infinity there. It's going to come up, it's going to have a turning point here, and then it's going to go down again. And this is going to come to here, have a turning point, and go up again. Something like that. It's actually approaching the line y equals x here. I know that because this is approximately x squared on x, which is x. So, yeah. but I don't think you did oblique asymptote in your course. So, yes. One thing that might happen, what if, always good to ask yourself what would happen if it was different, because then you get the added benefit of more examples. Something that might happen is it's just easier to do another example. Some functions, like that function there, some functions will not go to infinity when you go, the function value won't go to infinity when the function goes to infinity. So let me just do the end behavior. Key point that I need to say aloud that I didn't say earlier, that end behavior is based on the original function, not on the derivative. The end behavior of this function is, well, let's see what happens. The limit as x goes to infinity of 3x plus 1 over a 2 minus x. If I use L'Hopital's rule, and differentiate both the top and the bottom, I just get minus 3. Because the derivative of the top is 3, derivative of the bottom is minus 1, you get minus 3. So this function, when x goes to infinity, is minus 3. So when you do your sign diagram, it won't go to infinity, it'll go to minus 3. So that'll happen at minus infinity too. Differentiate the top, differentiate the bottom, still minus 3. So this function flattens itself out at the edges. Yep, we can look at its asymptotes. So there's a vertical asymptote at x equals 2, because that's when it's undefined. As x approaches 2 from the left, the top of my function will be 3 times 2 plus 1, which is 7. The bottom will be 2 minus x. Okay, so just a second. X is coming towards 2 from the left, which means x is just a little bit less than 2, which means 2 minus x will be positive. So that was my reasoning. X is less than 2, 2 minus x must be positive. And so therefore f of x approaches 7 over infinity, but 7 over plus infinity. 7 over 0, but 7 over plus 0, so plus infinity. And as x approaches 2 from the right, 3x plus 1 still approaches 7. 2 minus x approaches 0, but this time from the negative side. And so therefore f of x approaches negative infinity. There are some functions that will, it's common that it will be plus infinity on one side and negative infinity on the other, but there are some functions where it will be plus infinity for both. For example, if it was on x plus 3 squared to begin with, 2 minus x squared, the bottom would be positive no matter what, and so it would always go there. Okay, and so I've got my asymptotes, I've got my end behavior, I could figure out my derivative, but it's not going to have any turning points. So I'm most interested in just making a point about this. What was it, 2? So I'm not going to fill in my f double dash if you don't mind. here it's going to, if you look at my end behaviour, it's going to -3. And this does not tell me whether it's going to -3 from above or below, sadly. Which is why I need to do my derivatives. Alright, I'll do them. Increasing, decreasing. So f dashed x, let's see, f of x was 3x plus 1 on 2 minus x. So derivative of, so we've got the bottom squared, keep the bottom, differentiate the top, then keep the top, differentiate the bottom. So we've got 6 minus 3x minus 3x minus 1. And so we get 6 minus 3x plus 3x which is 7 over 2 minus x squared. So that's never 0. So I don't have any turning points. So f dash x solve, which is that 7 over 2 minus x squared is 0, which is 7 equals 0, which is no solutions. There's no way for 7 to be 0. And so we do have a critical point when x equals 2, but we've already got that in our sign diagram. And so now we figure out what happens in each zone. So is it 2? Over this side, let's see, when x is equal to 1, f dashed x would be positive. It's always positive, basically. So we're just going to get positive. When x is equal to 3, we're going to get f dashed x equals positive because it's always positive. Okay, so cool. We can now finish our sign diagram. F dash f. And this was 2, which is one of those, minus infinity, infinity. So we know in here f dash is positive, f dash is positive. So we know that what's happening is it's coming up here, and on this side it's going to 2 from the left was plus infinity, and over this side it was going to -3, because that's what we figured out just here with the asymptotes. With the end behaviour back here it went to -3, and this way it was still going up, and this one was going to minus infinity, and over here it was going to -3. And so as a quick crack at what the function looks like, there's an asymptote here. It goes to plus infinity and it comes down and it levels off at -3. And this one, it comes up to -3 from below, like that. So we know it goes down to minus infinity near to the asymptote, and it approaches -3 from this side, so it's coming up from below. If we were very unlucky, our function might actually come and turn and then come down again, but we would have known that because there would have been another turning point. So because we know that it doesn't come up and then come down again because there's no more turning points. So, yes. And actually I would have expected this to look like this. This is the same shape as the graph of 1 over x, roughly, which is what we had. We had something that was 3x plus 1 over 2 minus x. If I had been very, very sneaky and written the top in just the right way, I would have had constant plus something over 2 minus x, which is why it comes out the way it does. So, yes, I hope that helps. And that's probably quite enough today. Thank you very much.